Good morning and welcome to this the lecture number 25 of the course Stochastic Hydrology. If you recall, in the last lecture we introduced the concept of frequency analysis. So, when we are dealing with extreme events, for example, high flows or high storm intensities or low flows which result in droughts and low rainfall values and so on. So, essentially when we are dealing with extreme events, we would be interested in answering questions such as what is the frequency of occurrences of a given magnitude of flow, for example. And that is when we define the recurrence interval, which is the time duration between occurrences of two extreme events of given magnitude. For example, the flow exceeding a value of 5000 cubic meters per second. What is the recurrence interval between such consecutive occurrences? And we also introduced the concept of return period, which is actually the expected value of the recurrence interval. When we say a return period of 20 years for a flood flow, it indicates that once in about 20 years on an average we may expect such an event to occur. Then we went on to define the probability of such an event, which is probability of x being greater than or equal to x t, where x t is the magnitude of that particular flood, let us say, and that is given by p, which we showed it to be 1 over t, where t is the return period. Then we also answered the question that the probability that a t year return period event will occur at least once in n years is 1 minus 1 over t over to the power n. What does this mean? This means that we have a t year return period event, let us say 20 year flood, but we are interested in getting this the probability that this 20 year return period flood will occur at least once, let us say next 10 years or next 15 years or next 50 years and so on. So, that probability is given by 1 minus 1 over t to the power n. So, this is the concept that we have introduced in the last lecture. We also solved a numerical example to demonstrate these various concepts that we developed. Now, we will proceed further and look at what is the type of data that we use for the frequency analysis. Say for example, we have monthly data for last 20 years collected at a particular location. We can use the entire data as it is and then carry out the frequency analysis, or we may put a threshold value and carry out the analysis on all those values which appear above the threshold value and so on. So, there are different ways of constructing the hydrologic series on which we carry out the frequency analysis. Let us look at some of these. For example, we may consider the complete series, that is whatever observed values that we have, we constitute a series out of that and then call it as a complete duration series and carry out the frequency analysis on the entire series which has been observed. You may have a daily record for last 20-25 years, you may consider all the daily record and then carry out the frequency analysis. So, such a thing is called as a complete duration series. However, mostly we will be interested in the partial duration series. A partial duration series is a series of data which we select after putting a threshold value. Let us say we are interested in flows above 2000 cubic meters per second. So, we put a threshold of 2000 cubic meters per second and then pick up from the observed data, you pick up all those values which are above 2000 cubic meters per second and then construct a series out of that. That is called as a partial duration series. We also have a commonly used series called as annual exceedance series. The threshold that we put in the case of partial duration series. Let us say you adjust the threshold in such a way that you get exactly those many number of values as you have the number of years of data. Let us say you had 40 years of data, you put the threshold such that you get 40 such values above the threshold. Note that these 40 values need not correspond to 1 per year, simply 40 such values we get. Maybe some years may have 3 such values, some years may not have any value and so on. So, we get 40 such values when we have 40 years of data, and then we form what is called as a annual exceedance series. Annual exceedance series is also very commonly used for frequency analysis, but the most commonly used series is the extreme value series. That is, it includes the largest or the smallest value occurring in each of the year. Like we discussed in the last lecture, every year you pick up simply the maximum value if you are interested in high extremes frequency analysis, or if you are interested in the low extremes, you simply pick up the minimum value occurring in every year. So, let us say you have every 15 minutes of data, as I explained in the last class, 15 minutes you are recording the stream flow at a particular gauge. So, every hour you have 4 such values, and every day you have 4 into 24 such values, and therefore, every year you will have 4 into 24 into 365 such values. Out of these number of values, you pick up just one value, namely the maximum value that has occurred during that year, and use these maximum values for carrying out the frequency analysis. If you had 40 years of data, you pick up one value corresponding to each of these years, which consisted of those 4 into 24 into 365 values. You pick up one value. Like this, you pick up 40 such values and then carry out the frequency analysis on these 40 values. So, these are different ways of constructing the data series on which we carry out the frequency analysis. To make it more clear, we will see one by one. What I mean by complete duration series is the entire time series that you have observed. Let us say this is an example where we have monthly data for 10 years, making it a total of 120 values. Of course, 10 years is a small duration. This is I am just showing it as a example. When you have monthly data for 10 years, you have the time series like this. You consider the entire time series as has been observed for the frequency analysis, and such a series is called as a complete duration series. For the partial duration series, we put a threshold value, let us say 20,000 qmax. We say that anything higher than 20,000 qmax is considered for the series. So, some years may have 1, 2, 3, 4 like this, and some years may not have any or may have just one. So, we pick up all those values which either equal 20,000 or exceed 20,000 and construct the series. This is called as a partial duration series. So, in this case we will consider only these values which are above this threshold value, and this threshold value is called as a base value. In the annual exceedance series, we still put a base value or the threshold value as we did in the partial duration series, but we select the base value such that we obtain these values which are above the threshold. The number of such values will be equal to the number of years of data. In this case, we had 10 years of data. So, we put such a threshold value such a threshold value that we get exactly 10 values above the threshold value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Some of the years may have 2 such values and some of the years may not have any value above the threshold value, does not matter, as long as you get 10 such values totally, you call it as the annual exceedance series. What happens in the annual exceedance series? For example, you consider these two events. The flood that has occurred or the maximum value that has occurred here may have produced this maximum value also in terms of its ability to saturate the soils, and therefore, a high intensity rainfall occurring immediately after that may have caused this flood also, and therefore, these need not be completely independent events. Similarly, these two need not be completely independent events. But for our frequency analysis, we have assumed that all of these events that you are picking up for the analysis are in fact independent and identically distributed, and therefore, we must have enough justification to assume that these events are in fact independent. Then in the extreme value series, all we do is pick up the extreme values. Let us say we are interested in the maximum values, simply pick up the maximum values occurring every year. So, if you have 10 years of data, you get 10 maximum values like this, pick up those 10 values and then constitute the series for frequency analysis. So, these are several ways of constructing the series that we consider for the frequency analysis. As I mentioned, the annual exceedance series and the extreme value series are the most commonly used series for carrying out the frequency analysis. The concept of the return period that we introduced in the last lecture was based on the annual maximum or the annual extreme series. So, the annual maximum or minimum series, which has the largest or the smallest annual values, we introduce the concept T return period from annual maximum series, but this can be related to the annual exceedance series by this expression given by Chow in 1964. That is, the return period T of the event from an annual exceedance series is equal to log T by T minus 1 raised to the power minus 1, where T is derived from the annual maximum series. So, T is equal to 1 by P is what we derived in the last class, where P is the probability of x being greater than or equal to x t, or probability of exceedance of that event, and from that you have the T, and from T you can get T e for the annual exceedance value. The annual exceedance series, as I just mentioned, may have more than one event occurring in each of the years, in some of the years, and therefore, the series that you have just constructed as the annual exceedance series may not really be independent, the values may not be really independent. So, it may be difficult for us to verify that all the observations are independent. The occurrence of a large flood, as I just mentioned in the annual exceedance series, let us say a flood occurred in the month of June and a flood also occurred in the month of July. The July month flood may not be completely independent of the June month flood, whereas if you are looking at the annual maximum series, what we would have picked up, let us say between June and July, July was the highest occurring in that particular year, we would have only picked up the July month flood for that particular year. In the next year, it may have occurred during the October month, and therefore, the two floods may be totally unrelated. And then as the return period becomes large, let us say that from 10-year return period to 20-year return period to 100-year return period to 1000-year return period and so on. So, as your return period increases, what is happening to the probability of occurrence of the extreme events? Remember, P is equal to 1 by T when we said the probability that we are talking about there is the probability of occurrence of that particular event in a given year. So, probability of occurrence of a T year event in a given year is the probability that we are talking about. So, as your T increases, 1 by T decreases. So, 1 by 100, 1 by 1000 and so on. So, as T increases, the probability of occurrence of that event in a given year decreases, and therefore, as the return period increases, the results that you get from the frequency analysis from annual exceedance series and the annual maximum or minimum series, they tend to converge. So, there is not too much of a difference whether you use the annual exceedance series or the annual maximum series for large T. However, for small t, for example, if you are looking at urban stormwater drainage, where your return periods will be of the order of 5 years, 10 years and so on. Now, it is in such situations that the choice of the particular type of series, whether it is annual exceedance series or the annual maximum series, that becomes important. Now, we have also seen in earlier lectures the extreme value distributions, which deal with extreme events, and by extreme events we mean either peak flood discharge in a stream, or maximum rainfall intensity, or minimum flows and so on. So, given any time series, we may be interested in only the extreme values recorded, and we fit the distributions for such extreme values, and these are called as the extreme value distributions. In fact, in the last lecture also I showed what we would be interested in such situations is really towards a tail of the distribution. Let us say you have the distribution like this of the random variable x, and then you are interested in high flows. Let us say that this is x t that we are talking about. So, we are interested in this region, which is the tail of the distribution, and these values is what we will be considering in the extreme value distribution. So, we are essentially putting fitting distributions to the extreme values, and then talking about probability of x being greater than or equal to x t, which is actually this area, and so on. The extreme value distributions that we so formulate are derived from the parent distribution, or are a function of the parent distribution. So, depending on whether the parent distribution is bounded in this direction or is unbounded in both the directions and so on, we get different types of extreme value distributions, as we have seen in one of the earlier lectures. So, in the case of hydrologic extremes, we may be interested in, let us say, study of peak flows, where we use the largest flow values recorded at a gauging station, or if we are interested in low flows, we may simply pick the smallest observed flows in a particular stream and so on, and then formulate the series corresponding to these. Depending on the parent distribution, there are three types of extreme value distributions that we normally use. One is the extreme value type 1, EV1, it is called as EV1, in which case the parent distribution is unbounded in the direction of the desired extreme. Let us say you are talking about maximum flows or the maximum values. So, the distribution is unbounded in the direction of the maximum flows, and all the moments of the distribution exist, because we will be interested in distribution being unbounded as well as the moments being moments existing. In such a case, we call it as extreme value type 1 distribution. In the case of type 2, the parent distribution is unbounded in the direction of the desired extreme, but all the moments of the distribution do not exist. In the case of type 3, normally we use extreme value type 1 and extreme value type 3. In the type 3, what happens? The parent distribution is bounded in the direction of the desired extreme. Let us say you are looking at low flows. Low flows generally, in hydrology, most of the variables that we consider are all non-negative, and therefore, they are bounded by 0. So, when you have a distribution which is bounded by 0 and you are considering the distribution of the low values, then you use extreme value type 3. So, typically the extreme value type 3 is used for low extreme values, minimum values, whereas extreme value type 1 is typically used for maximum flows or maximum values, although it can also be used for in some situations it can be used for low values as well. Let us look at the extreme value type 1 distribution. The type 1 distribution, the CDF or the cumulative probability distribution, cumulative distribution function f of x is given by this we have seen earlier. Just for completeness sake, I will put it again: exponential minus x minus beta over alpha, where beta and alpha are the parameters of these, and it is defined for the entire region minus infinity to plus infinity. These parameters alpha and beta are estimated thus: alpha is equal to root 6 s divided by pi, where s is the standard deviation, sample estimate of the standard deviation, and beta is equal to x bar minus 0.577 alpha, alpha given by this, x bar is the sample mean. So, this is how we estimate alpha and beta. Once alpha and beta are given, the f of x is completely defined. This is the extreme value type 1 distribution. As I said, it is unbounded on both the directions. So, it is minus infinity to plus infinity. For convenience, look at this expression minus x minus beta over alpha. So, we use a transformation y is equal to x minus beta over alpha. We use this transformation and then we express the CDF. This is a linear transformation. So, we write f of y is equal to exponential minus y, and y varying from minus infinity to plus infinity from this. This is commonly known as the double exponential distribution. You have exponential minus y, double exponential distribution. It is possible for us to solve for y from this expression, and then we do this to get y is equal to minus ln 1 divided by f of y. Such type of CDFs are called as, such type of functions are called as invertible functions. That means, given f of y, I am able to express y in terms of f of y. But not all CDFs have this property of invertibility. Because the extreme value type 1 distribution, the transformation of that into the double exponential distribution is invertible, we use this property and then carry out the frequency analysis. The frequency analysis that we carry out directly on based on the CDFs using the property of the invertibility are actually analytical methods, which means analytically we should be able to determine y t for a given return period t, because we will know from a given return period t, we know the probability of exceedance, probability of let us say y being greater than or equal to y t, and from which we know f of y. From f of y we get y. So, this is just a straightforward analytical method which is possible only when your CDFs are invertible, in the sense that we will be able to express x in terms of f of x or y in terms of f of y in this particular case. Because our probability small p we defined as probability of x being greater than or equal to x t. This is the magnitude corresponding to the return period t, and this we have shown it to be 1 over t. So, small p, which is equal to probability of x being greater than or equal to x t, is 1 by t. What is probability of x being greater than or equal to x t? We can write this as 1 minus probability of x being less than or equal to x t, because it is a continuous variable. It does not matter if you write small less than or equal to. So, this will be equal to 1 over t. This is our f of x. So, we write this as 1 minus f of x t, this is f of x t. So, 1 minus f of x t is equal to 1 over t. So, from this we write f of x t is equal to 1 minus 1 over t, or this will be equal to t minus 1 over t. So, from here y is equal to minus ln 1 over f of y. Now, this f of y, using the expression for f of y here, f of x t in this particular case, I write it as y is equal to minus ln t over t minus 1, because 1 over f of y. So, given the return period, straight away we will be able to estimate the corresponding y. Once you know y, you know the transformation that we have used, that is x minus beta over alpha. Beta and alpha are estimated from the sample, and therefore, we should be able to get the corresponding x value. What I mean by that is that let us say you have observed stream flow data which are x, observed annual maximum stream flow data which are given by x, and then from the observed series you would have estimated alpha and beta from these expressions. So, the parameters are estimated, and therefore, you have used this particular transformation and fix the return period for which you want the corresponding value. Let us say you want a value corresponding to 100-year return period. Then corresponding to the 100-year return period, you get y. This is t is fixed as 100-year, and therefore, you get y. Once you get y, you can get x from this, because alpha and beta are known. So, this is how we obtain the magnitudes corresponding to a given return period when we are using the extreme value type 1 distribution. Let us carry out a simple example now. The same 45 years of maximum discharges that I considered in the last lecture, we will take it now, and then we will first formulate a model in the sense we will formulate the CDF expression for the CDF based on the parameters, and then from that we will calculate the 20-year and 100-year return period discharge values, that is the discharge values corresponding to return periods of 20 years and 100 years. So, this is the data from 1950 to 1994, there are 45 values here. The Q that is shown here is the annual maximum discharge in Qmax. All these values are in Qmax. Then what we do is we first calculate the mean and the standard deviation of this data. So, the mean comes to be 756.6 cubic meters per second, and the standard deviation is 639.5 cubic meters per second. With this we calculate alpha, which is root 6 s by pi, and s is 639.5. Therefore, alpha comes out to be 498.6. Then we calculate beta, x bar is 756.6, s is 639.5, and this beta is given by x bar minus 0.577 alpha, and that is what you get here. Alpha is 498.6. So, you get beta as 468.8. So, once you have fixed the parameters, once you have determined the parameters alpha and beta, the f of x or the CDF of the extreme value type 1 distribution can be directly written, and that becomes the probability model for us. So, the probability model is f of x, which is given, which gives probability of x being less than or equal to x is equal to exponential minus x minus 468.8, which is beta, x minus beta over alpha, and for this is defined for x ranging from minus infinity to plus infinity. Then we go to the transformation y. So, this is the probability model. Remember, this gives probability of x being less than or equal to x, and what we would be generally interested in when you are using extreme value type 1 distribution is probability of x being greater than or equal to x, and that is given by 1 minus f of x. And using that we have obtained this relationship y is equal to minus ln t by t minus 1, where y is the transformation x minus beta over alpha. So, for a given t we calculate y. Let us say you are interested in this particular example, we are interested in getting the return the stream flow corresponding to the return period of 20 years. So, for t is equal to 20 years, we just substitute t is equal to 20 years here, 20 here. So, y 20 is minus ln 20 by 20 minus 1, which is 2.97, where y is x minus beta over alpha. Once you get y, we use this expression to get x 20. So, x 20 will be simply equal to beta plus alpha into y 20. In this case, that becomes 1950 cubic meters per second. So, for the data that we have here, you just look at this, we are getting a value of 1950, 1950 for a return period of 20 years. There is one value which is more than that. Other than that, you do not see there is another here. Other than that, you do not see values that have exceeded this in the record 1950. So, 1950 cumex is a value that you can expect at this particular site to occur once in about 20 years in a long period of time. So, this is the interpretation of the flow corresponding to a return period of 20 years. Similarly, for t is equal to 100 years, we use the same method and get y is y 100 as 4.6 by putting t by t minus 1 and taking the logarithms, double logarithms, you get y 100 is equal to 4.6 and the corresponding x 100 will be equal to beta plus alpha into y 100, beta and alpha remain the same and you get this as 2762 cubic meters per second. Between the 20-year return period and the 100-year return period, there is a significant difference. 1950 cubic meters per second is what you get for 20 years and for 100 years you get 2762 cubic meters per second. From the data of 45 years now, we are now able to say, using the extreme value type 1 distribution, we are now able to say that if you are using that particular data to construct a reservoir which has to pass over a 100-year return period flow, then this is the value that you have to use for the design of the spillway. That means, the spillway should be designed to pass a discharge corresponding to 2762 cubic meters per second, which may not have occurred in the data at all, although in one case it has occurred. But even if it has not occurred in the data at all, from the extreme value type 1 distribution, we should be able to assess or estimate the value for which you have to design the spillway, if it has to pass a 100-year return period flow, and that is the idea of the frequency analysis. Extreme value distributions, as I said, have been widely used in hydrology, especially for floods and low flow distributions and so on. Typically, we use extreme value type 1 or the type 3 distributions. The type 1 distribution, as I just demonstrated, are commonly used for high flows, flood peaks, maximum discharges, maximum temperatures and so on, maximum annual temperatures and so on. Whereas, the extreme value type 3 distribution, which is also called as a Weber's distribution, is most commonly used for modeling low flows or low values. And low flows, as you know, are important for drought analysis, or in the case of water quality, stream water quality and so on, we will be using the low flow analysis. So, it is important for us to assess low flows corresponding to certain return periods. The extreme value type 1 distribution is also called as a Gumbel's extreme value distribution. A concept of general extreme value distribution also exists, where you have an expression which encompasses all the extreme value distributions that we generally deal with. That is called as a general extreme value distribution. I will not be covering that in this particular course, but remember that this different types of distribution, extreme value distributions that we talked about, type 1, type 2, type 3 etc., they can all be combined into some general expression to give a general extreme value distribution. Now, so far what we did in the frequency analysis, we knew the distribution, and from the distribution we could invert, in the sense that given f of x, we would be able to express x as f inverse x f of x, and then carried out the frequency distributions, frequency analysis. However, it is not always possible that the CDFs are invertible, in the sense that you may not be able to express always x as f inverse of x. The form of f of x may be such that you will not be able to readily invert the f of x to obtain x. Say for example, probability distributions such as normal distribution, log normal distribution, Pearson type 3, log Pearson type 3 distributions, these are not invertible. However, they are most commonly used in many of the hydrologic analysis for frequency analysis. And therefore, we develop an alternate method for calculating the maximum magnitudes of extreme events, and this method is by using frequency factors, what we call as frequency factors. What is the logic in this? Essentially what we do there is that we will use the distribution, the parent distribution like this. For example, let us say we are interested in x t, let us say we are talking about normal distribution, and then we are looking at high extreme values x t. And because we cannot get x as a inverted value from f of x, that means because capital F of x in the case of normal distribution is not invertible, not readily invertible, I will say, not analytically invertible in any case, not readily invertible. What we do is that we take this extreme value as a deviation from the mean. So, we write this as mu plus k into sigma, some k times sigma. This is mu here, this is the mean, and this is x t, and we are interested in getting to this value, that is we are defining this as an extreme. So, we write this as mu plus k into sigma. Now, x t depends on t, which is the return period. So, we write this as mu plus k t into sigma, and we are interested in the probability that x being greater than or equal to x t. So, essentially we are interested in this area of the parent distribution. What do we write this as? This is probability of x being greater than or equal to x t, and this is given by, from our fundamentals, x t to infinity f of x dx. That is the area under the curve from x t to infinity. So, essentially we are writing this extreme value as equal to mu plus some factor k t into sigma, and these factors are called as the frequency factors. So, k t we denote it as a frequency factor. As it is obvious, as your t changes or the return period changes, your x t changes, mu and sigma remain the same, your x t changes, therefore, your frequency factor changes, because you are talking about the deviation from the mean. So, k t is a function of the return period, and that is why we put this subscript t. It is also noteworthy that k t is also a function of the probability distribution itself. For the same x t value, let us say if your mu and sigma changes, k t will also change. So, k t is a function both of the return period, and therefore, we put t, and of the probability distribution itself. So, for a given probability distribution, you should have the factors k t for different return periods. And we use this concept of the frequency factors to get the get the magnitudes corresponding to given return periods. So, that is what we do in the method of frequency factors. So, we use the frequency factors and determine the magnitudes. So, like I said, we essentially express x t as mu plus some delta x t, this is the deviation, and this delta x t we write it as k t into sigma. I will just explain it again for completeness sake. So, what we are doing is for any given distribution, not necessarily normal distribution, we are writing x t here and your mean may be somewhere here mu. So, we write this as k t into sigma. So, this is k t into sigma. So, x t we write it as mu plus k t into sigma, and then for sample values you use x t is equal to x bar plus k t into s. So, knowing x bar and s, and if you know k t, we should be able to get x t. Now, how we determine k t for different distributions is a question that we will address now. So, essentially the method of frequency analysis using the frequency factors boils down to this expression x t is equal to x bar plus k t into s. S and x bar are estimated from your data and k t is known or can be derived or is available for a given distribution. Let us say normal distribution we have the k t for a given value of t. Log normal distribution we can derive k t for a given value of t and so on. So, given the distribution you know k t values and therefore, we know we will be able to get x t. What is x t? Again to repeat, x t is the magnitude of the particular variable corresponding to a return period of t. So, the derivation I am sorry, the frequency factor is, as I said, a function of both the probability distribution, the parent distribution, as well as of the return period. So, as the return period changes, your k the frequency factor changes, as the probability distribution changes, the frequency factor changes. Now, let us say from your original data from stream flow data, let us say you are converting it into logarithmic flows. If you are interested in the log transformed data, you can still use the same expression in terms of y t now. Y t is equal to y bar plus k t into s y, where y is the log transformed data series. So, you get from the log transformed data series the k t values remain the same and you get s y and y bar from the log transformed series and you obtain y t. From y t you should be able to get x t again back. As I mentioned, for a given distribution, the k values, the frequency factor values should be determined corresponding to several desirable t values. So, the k t relationship can be determined for a given distribution. There are methodologies available, we will not go into those methodologies, but we will use the results from such methodologies for some specific distributions. Now, this relationship, the k t relationship is fundamental to the frequency analysis using the frequency factor. So, for any distribution we should have this relationship, that means given a t, given a return period for that particular distribution, we should be able to get the corresponding k value. We will see how this can be done for the normal distribution presently. So, essentially what we do is from the historical data we obtain the moments, that is the mean and the standard deviation, and from the available k t relationship for that particular distribution we obtain the k t value and use these k t values to get the x t values. That is all that is there to the frequency analysis. A major question then is which distribution to use. Do we use the extreme value type 1 distribution, in which case we know that it can be done analytically? Do we use the normal distribution? Do we use the log normal distribution, log Pearson type 3 distribution, and so on? It is there that some judgment is involved and also there are analytical methods of estimating which distribution best fits the particular data, which we will cover in subsequent classes. But typically if we want to use a given distribution, we should be able to get the frequency factors if that distribution is not invertible. If it is invertible, we can always use the analytical method. So, we will just see now how we obtain, for example, the frequency factor for normal distribution. The expression that we are using is x t is equal to mu plus k t into sigma. So, x t is equal to mu plus k t into sigma is our frequency analysis expression. From this we can write x t is equal to k t is equal to x t minus mu over sigma, and we identify this as simply the standard normal deviate z. Recall that we wrote z is equal to x minus mu over sigma. So, this is simply the z value. So, you have the option of simply going to the table and picking up the corresponding z value. Given x t minus mu over sigma, you can obtain the z value corresponding to those particular probabilities. What I mean by that is, given the return period t, you know the probability p is equal to 1 over t, and from the probability you know the z value, and you know the f of z value, and from the f of z value you enter the table of normal distribution and obtain the z value, as we have done in our normal distribution calculations. You can refer to one of the earlier lectures where we discussed the normal distribution. However, there are also empirical expressions available for obtaining the z value corresponding to a given probability p. We will use that here, but I again repeat that this is not necessary. You can always use the tables, normal value tables, once you get the p values. So, once you fix the return period t, you can get p, which is p is equal to 1 by t. The z corresponding to a given return period with p is equal to 1 by t may be approximated using an intermediate variable w. So, we define w as log 1 over p square, the whole raised to the power half, for values of p between 0 and 0.5. We use this intermediate value w to obtain the k t value. In fact, this is an expression for z directly for the normal distribution. This expression that I am saying, I am writing it for z value here, and z is the same as k t in this case. Therefore, I write it for k t. So, we define first w knowing p. How do we know p? Because we have fixed the return period t. From p is equal to 1 over t, we get p. Once we know p, we can get w, as long as p is within the range 0 to 0.5. In most of the cases it will be. If it is not, we will see what to do. So, once you get w, you can get k t. Now, these are slightly cumbersome looking numbers, but they are obtained from some empirical relationships. So, you get from w you can get k t. Once you get k t, you can get x t, because s and x bar are known. We said this is valid for p is equal to 0 to 0.5. If p is more than 0.5, then what we do is, instead of p, we substitute 1 minus p here in this expression. Let us say p is equal to 0.6, then we use 0.4 here, 1 minus p, and then still use w, and then from w we get k t, and this k t we use it as a negative value with a negative value. So, when p is greater than 0.5, 1 minus p is substituted here for w, we use that w resulting from 1 minus p and obtain k t, but in the expression for x t, namely x t is equal to mu plus k t into sigma, we use k t as a negative value, and therefore, we write it as x t minus k t into sigma when p is greater than 0.5. When will p be greater than 0.5? When t is very small, because as t increases p decreases. So, when t is small, you may get a situation where p is greater than 0.5. So, that is how we address the case where p is greater than 0.5. The error in this formula is very small, of the order of 0.00045. So, this is the error in z that we are talking about, that is the standard normal deviate as obtained from this expression. That error is extremely small, as has been shown by these authors here, and that is a reference. So, for the normal distribution, estimate x bar and s from the data, and then for a given return period t, you obtain the probability p is equal to 1 over t, and from that you obtain the w value, which is the intermediate value. From w value you can get the k t value, and once you get k t, you know x t is equal to x bar plus k t into sigma, or k t into s if you are dealing with samples, and therefore, you can get x t. The same procedure we can also use for log normal distribution. So, the straightforward way of doing it is simply convert all your values into logarithm transformed values, and then use the same principle as we have done for the normal distribution. So, before we go into the example now, we will just try to summarize what we covered in this particular lecture. So, essentially we started with the introduction of frequency analysis, and we saw that the data series that we consider for the frequency analysis can be constructed in different ways. One is to consider the entire series, or the other one is to put a threshold value and pick up only those values which are above the threshold value if you are looking at high extremes. And the third one is you put the threshold values such that you will get those many values above that particular threshold as the number of years of data itself, that is called as annual exceedance series. The annual exceedance series is commonly used for frequency analysis, but the annual exceedance series, as I mentioned earlier on, suffers from the fact that the independence of the data cannot be ensured always, or you may not have a way of ensuring that the data series that you have constructed consists of values which are all independent of each other. The most commonly used series is the annual maximum or minimum series, where for every year you pick up exactly one value, which may be the maximum value or the minimum value, depending on your need, depending on the analysis that you are carrying out. Then once you know, once you have constructed the series, then you can go with the extreme value distributions, extreme value type 1 distribution, type 2 or type 3 distribution. In hydrology, most commonly we use extreme value type 1 or the extreme value type 3 distributions. If you are looking at the maximum values or the high extreme values, you typically use extreme value type 1 distribution, which is also called as the Gumbel distribution. From the CDF of the extreme value type 1 distribution, it is possible for you to obtain x t, which is the magnitude of that particular variable corresponding to a return period of t, because extreme value type 1 distribution is invertible. Similarly, we use the extreme value type 3 distribution when we are looking at low extremes, for example, low flows, low rainfall values and so on. The extreme value type 3 distribution is also called as the Weber distribution. There are certain distributions which are not invertible and which are also most commonly used in hydrology. For example, the normal distribution, the log normal distribution, log Pearson type 3 distribution, etc. Now, for these distributions we use the method of frequency factors, and that is why what we introduced in this particular lecture. The frequency factors, the basis for the frequency factors is that we take x t as a deviation from the mean. So, we write x t is equal to mean plus some factor k into sigma. So, it is deviating from the mean from by an amount of k into sigma, and k are called as the factors k are called as the frequency factors. Frequency factors are a function of the return period t as well as of the parent distribution itself. So, for a given distribution we should have a k t relationship, which means for a given return period we should be able to get k. And we saw that for the normal distribution the k t just corresponds to the standard normal deviate z. So, once you fix the t, you are actually fixing the p, and that is probability of x being greater than or equal to x t, and therefore, from this you can go to the normal distribution tables and pick up the z values. There is also an empirical relationship that I just introduced, from which you can get k t value. So, once you get the k t value, you can get the corresponding x t value. The whole idea of the frequency analysis is to obtain x t values, x capital T for a given capital T, which is the return period. We are interested in getting the magnitude corresponding to that particular return period. And for different distributions, we obtain the k t values and obtain x t values. So, we will continue this discussion in the next lecture. We will start off with an example of the normal distribution, numerical example, which will drive home the points that I have been discussing in this particular lecture. Thank you very much for your attention.